So let me start. Others will be joining accordingly. So good evening. I'm Pulak Viswas. I'm taking the live session number 2 for this numerical methods course, finite difference approach, that is taken by Professor Amya Kumar Nayak from the Departments of Mathematics, IIT Roorkee. So let me start. I guess the screen is visible. So yeah, let me start with the truncation error. And in most of the problems that is considered in the numerical methods, we usually use this Taylor series. If you know the expression, let me again, it is already written here. So it is having this kind of forms, but we do not consider all the terms. We truncate after a certain like number of terms, and whatever terms is left, that comes under the error in order to represent the function. So suppose for this function, if we truncate after this, the fourth term, 1 2 3, and this fourth term, so this will be the error. And its order, like what is the order of the error, it is represented in terms of the factor that comes here, the h to the power 4. So the order of this error will be h to the power 4. Now we use this Taylor series to construct a to approximate the derivative terms. Suppose this one, the first derivative. For first derivative, what will happen? For first derivative, like we neglect these terms and only consider these three to calculate this first derivative term for the forward difference scheme. So there you find that this term is there, like the minimum power of h that is left in constructing this approximation. Now we, if we divide by this h, so h will be coming all over and it will be gone. So we are lefting the terms, uh, the minimum power of h, that has not been considered, that comes as h. So the order becomes h. Similarly, if we do the same for backward difference, we will again get this thing, the order as h. But if we do it for central difference, then we will find that we have to truncate the h square term, whatever term is there, including the h square, in a similar way for the second derivative as well. Hmm. So suppose I want to show it for this central difference one. So this is the formula, but how we can actually compute this thing? So if we use the Taylor series formula, fx plus similarly this one. Now if we subtract these two things, then what will happen? These two getting cancelled, these two again getting cancelled. But if we keep the other third term as well, similarly here, so then it will become positive. So you see what is happening, minus these two gone, this is becoming 2h df dx, again these two gone, but these two adds up. Like if we truncate up to this only, still this term remains. In order to like, now if we express like this the derivative term, so it is coming like this. Maybe if we keep other terms, that might also occur. So for the central difference, we choose the formula up to this formula. So we neglect this term. So the order of error becomes h squared, as you have seen here. So in this way, the order of the error is decided, like for a particular approximation using some central difference or whatever we use. It comes from this left term, whatever is there, that comes as the order of the error, truncation error. I guess your confusion is now cleared for the truncation error. Okay, so I will be actually solving the questions. For some of these I have already calculated, and some I'll be doing in the session, during the session. So now it is asked that what will be the order of truncation error. Now I will be like solving few problems in which that may be already covered in yesterday's, like Saturdays. Okay, so after solving these questions, at the end of the session I can take your questions, whatever doubt is there, and try to answer those. Okay, so I think you have like we have calculated for this expression for the last session as well. So there, like, we can represent this as a Taylor series, and for each of the term we can expand it using the Taylor series formula. And if we ultimately sum these terms, if you see, this term is getting cancelled, like 0 is multiplied against this term, this is some value, again the second term is multiplied with 0, and this term is also multiplied by 0. But if you consider like up to the fourth order term as well, if you kept that thing here up to h4 term, so it is not becoming 0. And now 6 delta x is divided in this formula. So if we divide it, this one 6 delta x, yeah, so this will be gone, but this term will be remaining there, not this term actually. Yeah, x to the power 4 will come, and at the bottom delta x, so delta x cube term will be there. So order of the truncation error will be this one, h3. I think you have mentioned, yeah, that one will be the truncation error for this problem. And yeah, in the last you also asked that up to which term we should consider for this. Yeah, you can see that up to if we keep up to fourth order term, it is remaining here, so we have to truncate this one in order to get some expression for the remaining terms from the remaining terms, and that was coming as the first derivative of u. Yeah, after cancelling whatever term is left, like here you see the third term is getting cancelled, like it get vanished because of this 0 coming at the top. Like now if we think like, okay, fourth term will all like the term against the fourth order term, it will be again 0, then we have to go for the next term, like maybe for the h fifth term it is becoming non-zero, so we have to see that up to which term it is coming non-zero. So if it comes non-zero, then accordingly the truncation error will be of that order or one less depending on the expression. Okay, yeah, so error is related to that, like up to, so this is for the derivative term, and like for derivative term whatever we are trying to represent this term in terms of like functions from the Taylor series expansion, and whatever term we are left, like we are neglecting, that comes under the order, whatever term, so that is comes under the truncation error. Yeah, now suppose this is the diffusion equation or the heat equation. So here it is mentioned that the for implicit scheme, what will be the truncation error, because now we have both like derivative with respect to time as well as space. So the order, yeah, order will be different for time and space. So if as as you have already said that backward difference approximation is used for time derivative and central for the spatial derivative. So like if you use backward, as I have shown here previously, for backward the order is coming as h, and for central it is h squared. So from this so what will be the answer? This one, this one. So this will be the answer for this question. Now if I write the scheme for this as well, so what will be for backward? Suppose I'm representing it with I and n. I for spatial domain and n for time domain. So the equation is del u del t equal to alpha del 2u del x2. So can you tell me the expression in terms of using this I and n? We can represent a function like this: ith position at nth time. Sir maybe represented this as I comma j. So I'm using this expression to represent the value of the point at the grids, spatial as well as the time temporal. So if you use the backward, and this is derivative with respect to time, so n maybe n plus 1. Yeah, yeah, like if I let me tell you, first I need to like simplify this equation. Okay, yeah, now it is actually then arranged, like rearranged into some equation, and like if we assume this term as r, so what is coming? 1 minus, no, n, I'm using n for time, and I for n for time, and I for the spatial position. You can use anything, any notation. You can also use pq, maybe you should be consistent. Yeah, but current point is n plus 1, so that will be cleared when we simplify this equation. Hmm. In the spatial term we also need to take, yeah, that is there. So this one is correct or not? Tell me. This special one, whether I should put in plus one or in minus one. Okay, let me check once. Like if I use this one, whatever is there, forward, like forward for this one and central for this one, then what is happening? Yeah, ask whatever question is like you have. So see, what I'm observing that if I use the forward like difference for the time derivative and this one like center difference for the special derivative, we can represent the next iteration value at ith position like n plus 1. We can calculate from the values all from the past positions n and n. But as you are suggesting, like that if I use n plus 1th as well for the this one, n plus 1. Yeah. Now you see the scheme becomes like this. Mm, this one R This whole thing is R. One minus R, then no, minus. Yeah, plus. Yeah, the scheme is coming like this. And from here, like the only the value is known is this one. And this is past. And these are the present values at different locations. But we cannot solve this in one step. Like we cannot directly use this value to calculate the like for the next iteration value. Like we could have used for this one. Like if we know at ith position or whatever grid positions are there, like different grid positions, if we use those values, we can calculate for the next step. But here at different locations, the equations is there. Like the equation includes n plus 1th term for different grid positions, I plus 1, I minus 1, and that and this one is known in this equation. So this type of problem is actually solved using forming a matrix. So one matrix comes, some a times, suppose un plus 1 comes, and here un, some vector is there, and we can solve this inverse problem to calculate the values of this vector. Maybe if we represent the vector like this. So this is I just wanted to mention you. You can solve this like this after forming this scheme for this implicit scheme. Similarly, for like Crank Nicholson, there you also find something like this. Okay, like this is the equation, and you want to find the solution to this equation, and there should be some domain of x, maybe 0 to 10 or maybe minus 10 to 10, whatever. So some domain will be there. Suppose minus 10 to 10. This one is the x, and also you maybe want to calculate the y's value at different times. Maybe your starting time may be equal to 0, and there may be some end time. up to which you want to find the solution, like what is happening with time with this to this variable u. It may happen that suppose your initial condition for the u may be some Gaussian function, suppose. So this is for particular time t equal to 0. This is your initial condition, and there may be also boundary condition at these two ends. Suppose they are 0 for this case. Now, like you want to solve like what will happen at some other t equal to maybe t1. So if you solve that, you will actually find that this type of solution will be coming for this t1. Again, if you take another time t2, yeah, ask, like it will decrease. And now your like different solution vectors. Suppose if I represent at all x at time, maybe this one is t0. So t0 was your blue, this blue Gaussian, and maybe let me give it a different color. So your this one initial condition will be this blue Gaussian, and your solution vector like at time t1, that will be this black Gaussian. But it will be changed, like it was sharp, it will like it becomes flattened. Again for like u t plus 2 another time, your Gaussian will be this further flatter than this one, this green. So this type of solution vector will be coming at for each spatial points, and your spatial domain ranges from -10 to +10. At different x values, you will be having different y values depending on the time, if this is the time direction. So these will be different solutions. This type of solution will be there. So now you can do this for using explicit scheme. Now if you use the explicit scheme, so this is coming, the formula is coming like this. Here you find like you find a simple formula, like for any point, maybe for I you may choose -10 or maybe 0. Suppose you choose 0, you can also choose like 5 or something, -5, whatever. So I may be 0, and this may you like this one maybe t1, where t1 is I have represented here as t1. That t1 may be your previous time plus delta t, delta, yeah, delta t, this t1. Yeah, so for next value you can calculate it using the previous values at ith, at I plus 1th, I minus 1th, again ith. So if you want to calculate as 0 for this one, next stage, so at this point the value will be calculated using one step ahead, one step back, these values. So suppose these three values will be used, and along with the delta x and delta t, these two parameters, you can calculate the this one at the 0th point at the next time, this time. Similarly, you want to like if you use explicit method, you can use like this: I plus 1, I minus 1, these three only, and you can calculate that. So using implicit method, you also want to calculate that one, like For 0, what will be the next value, like 0th value at different time, next time. But you cannot calculate a simple formula like this for the explicit scheme. You can directly put the values and obtain the value as a 0th point, as I have mentioned. But here you have to solve one matrix type of one matrix problem, inverse problem. Then you can calculate this thing. Now suppose your domain starts from like, let me draw a domain for you. This may be I plus 1, I minus 1. This may be n plus 1. So you want to calculate your value, suppose at I and n plus 1. Or in place of I, j, k, if I write in terms of numbers, suppose 1, 2 and 3, and whatever, like for time we can keep n variable. So if I use this equation now, what will become having? I plus 1 means this one was I plus 1 means u3, n plus 1, r value you know, plus plus 2r, ith value is 2, n plus 1, minus r, u, I minus 1 means 1, n plus 1, and this one will be your 2 and n. Similarly, suppose there is another point, fourth point. Okay, that for that case your I will be 3. So that time your this one will be u4. U2. Similarly, others will be there as well. So if you construct a matrix, like in order to find these values, you do not know these values you want to find. So minus r 1 plus 2r minus r 0 0 0 dot 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 0 minus r 1 minus 2r minus r. So this type of one matrix will be coming, and here your these values will be n plus 1, u2, n plus 1, u3, n plus 1, and here u1 n, u2 n, u3 n, these values will be there. And this matrix is now known to you. Like if you see these two equations, you can see like minus r into this one, minus r into this one into this one, this again, yeah, minus r3 into this one from this. So this type of matrix will be coming, and this will be your unknown vector. You want to find the use value at this level, and you have values provided initial condition at this level. So now you can solve like this. A, like if your this one is un plus 1 vector, and this you can solve. You can matrix inverse this one, suppose, then you can get this vector. So this was I was trying to tell you. And you can also keep this example in mind, like for diffusion with Gaussian as the initial condition, it decays like this. Okay, can you tell me like what is the correct for this correct option for this one? Heat equation del U del T equal to some diffusion constant will be there. So you know that A is correct, yeah. And let me again clarify this one. That delta T needs to be finer for Crank-Nicolson method for accurate calculation. So while it is not for explicit scheme, actually the stability problem comes only for the explicit case. For implicit and Crank-Nicolson, like they are unconditionally stable. Whatever value you choose for delta T or delta X, it is stable. So this is actually it should be reverse. For explicit, delta T cannot be any value. Some criteria is there, and that criteria is actually this one, delta T by this one, it should be less than half for the explicit scheme. But for Crank Nicholson, nothing is required, it is already satisfying the condition. And for Crank Nicholson, the spatial derivative is calculated at, no, this one is also wrong, so this one is correct. Okay, yeah, can I do this, solve this one, try. I think yeah, how we can compute this one, like what is the method or what is the criteria to solve this equation, I solve this problem. If you see this equation, here E represents the error, and it is at some, here it is represented in terms of Q. So this is the past or present, whatever. This represents error in that level. Suppose this one is Q and this one will be Q plus 1. So error propagates. Suppose you have some errors in computing these results. So this will propagate, like you are using the values of this level in order to compute at this level. So you can think that error will be propagated into this level because of the, like some error will be coming from the schemes and already you are using the erroneous values, so it will be propagated to that level. So and it is actually represented like this. At the next level, uh, defined like this. And in order to like get the answer, this is some matrix that is multiplied to this error at qth level. So for this the eigenvalue, it should be, what is the criteria like for eigenvalues? If this is some matrix A, maybe whole matrix, suppose A equal to this one, and it is already mentioned u is the eigenvalue of this mu, sorry, mu is the eigenvalues of this matrix. So its value should be less than 1. So from that you are actually like solving the problem, this problem. And it is already mentioned the mu is the eigenvalue, so it is coming like this. Mu is already given, that this is the eigenvalue of t, so you can use that. Now you can simplify this one, so you will get what is coming. Yeah, this one is correct. How to solve this one? Implicit method, this one is the scheme already given for the same equation, and Neumann stability criteria we have to apply. So in Neumann stability criteria, like for the using some schemes, here we have used like implicit method is used for approximating the derivatives, time derivative and spatial derivatives, and we found this one. So if I write this one again, yeah, that is why that symbol is little easier to understand, and the like in, and this can be used for 2D. Like let me say it, like if your function is a two-dimensional function, and you also like want to see the variation with respect to time, then it is actually represented as I, j and nth. I represents x, y and time, like that. The process is simple, like you have to put this one into the expression. Here it is p gives the spatial domain term, like spatial variation, this gives the temporal variation, and you have to simplify the equation and you can get the value for this xi. So can you try this one, like if you insert the value and simplify it, what is coming for this one, like I is your x and j is your time, so it will be e I beta. This I is different I, the complex number, and p is equivalent to this I. Your xi, this j plus 1. Yeah, you can do like this. Try to solve this one. J plus 1. Oh no, sorry, not j. It should, I should write q. Mm, q plus 1. Yeah, if we divide like all through with this one, as well as this one. This one, xi 1 means xi minus 1 equal to k. This one is coming. Now if I simplify it, And like you can find this one, uh, this live session things you can find. There is one section added, like in the swam portal. After the weekly feedback link, you will find one problem solving session. So if you click that one, so from there you will find the link for each of the sessions. What is the option? This one is r, k by 2h square. What is the value of this one? Like e power ib beta h plus e to the power. Don't tell me this one. I forget. What it comes? Cos minus sin or sin minus cos? Can you tell me like what is the value of this one? Yeah, I guess it is cos, but in the question it is given as sine. Sine squared. I think you can compute from cos theta to like cos to sine. Yeah. So this one will be like if you divide by 2, it is coming cos or what? Cos 2 r. This is cos beta h minus 1. Can we write it in terms of, yeah, we can write it. What is the formula? So there is some relation I forget. From there you can get the value. Then you can use that one and try it. Okay, you can try that one using the expression first and something. Again, a similar problem, like this is another equation, and this is called advection equation. You can use the here it is first derivative. So you can calculate like for the, and this stability is actually done for explicit scheme. So you can try. You can use the forward difference as well for you. So let me use that one. This one is central. Yeah, you can use central or maybe the forward as well for the special derivative. So this become your scheme. So again, in order to find the stability, you can use a similar to this type of expression. Mm, so for u maybe I n, you put e power I beta ph, and this is I to the power q. So if you put this into this equation, then you can find the value of this xi, and its value, like what is the criteria for what is the value of xi, so that this one is stable. You know that. So this is xi's value should be less than equal to 1, then only the scheme becomes stable. So you can try this one, put this value and simplify and find the value of xi, and there you can put some constant, like constants, to find out what is coming, like what is the maximum value of xi. If it is less than 1, then the scheme is stable, and that may give rise to some relation between this t and delta x, delta t and delta x. You can try this one later, maybe, or can you try right now, like what is coming? uh, I'm not sure actually, for like Okay, so there are two methods by which the stability is analyzed. One is this Neumann stability, and there is another method that is called matrix. So there, like, you have to remember this, like we have to replace these values, like as we mentioned with this one, like UPQ, it has to be replaced by this one. And if we replace this one and simplify in this way, then there will be some values of xi, and that value should be less than equal to 1. If it comes like that, then it is stable. Then this scheme, whatever scheme is you have used, this scheme is stable. Thus, suppose for this case I have used forward differences for both the derivatives, then you can put the value like this, and whatever value of xi will be coming from there, you can put this constant, like if it is less than 1, like now if you make it less than 1, so some relation will be coming between delta t and delta x, because these are the values. Here h is actually your delta x, r includes delta t delta x, so some relation you can find between this delta t and delta x. So one such relation is like this, as you have seen, this one. Like for explicit scheme, this condition should be followed, then it is, then the scheme is stable, otherwise it will be unstable. And what is actually meant by stability, do you know that one? Like what is meant by stability? So there is criteria. If the criteria is satisfied, the scheme is stable. But if it doesn't satisfy, then what happens to the solution? Yeah, like I was showing you for Gaussian, like diffusion, it should decay like this. But if your scheme is unstable, it may happen like it begins to oscillate. So oscillation is sin when the scheme is unstable. Maybe your result may be coming like, it may also go to negative. So when your scheme is unstable, so you can see that oscillations are seen in the result. Yeah, something like that. So you can try for this one. Like here, some option will be correct. You can use the formula to simplify, and whatever is there, that will be coming. Similarly, for this equation, like this problem, you can apply this constant to find the relation between delta t and delta x. What is coming? Something will be coming, and it differs for different scheme. If you could have used central difference for this one, then the criteria will be different. So you can try that way. So this thing, what is the answer for this one? We have already seen. Yeah. Which of the following is central finite difference scheme representing del del x with error of order 4? you can do this one. This will be a little lengthy. We have to try for each of these cases, and you have to find like when the error is coming of order 4. uh, you can, yeah, you can try it later. It will be time taking. Or we can use this thing, previous calculations, to calculate for the same. You can also find that central difference, like, yeah, something like that. If you use, suppose these two values, it may become forward or backward depending on the point of calculation. But when you want to calculate, suppose at the midpoint, but using the values at the two adjacent points, then it will be central difference. Actually, these are approximations. Like you want the value of the derivative. Suppose at this point, what you are doing, you are like telling that okay, I am taking u's value at the next point, x plus h, and at ux, and dividing it by the separation, and we are approximating this as the derivative. You can also do that using different points. Suppose this point and this point, and that time 2 delta x is coming automatically. You can also see from this figure. In that way, you can also visualize. So for this equation, oh, yeah, okay, okay, you can try this one later on. You have to try for different combination, and whatever term is left, that will give your order. But you have to find the what is when the order is becoming, like with which combination the order is becoming 4. You can try. The ninth. Finite difference representation of this equation, diffusion equation, crank Nicholson scheme. Yeah. So tell me, for crank Nicholson, what schemes I should use for this time and spatial derivative? For time, so have you computed this, or you know? So in crank Nicholson, what is okay? What is done? Like there may be one grid. These grids are like you want the solution. Yeah, you can ask. Okay. So in crank Nicholson, like in the previous explicit or implicit cases, you either use this level of values and compute directly to the other upper level, upper 2 points, because boundary condition will be provided on this too. And for implicit, like you are constructing one vector of values corresponding to this multiplied by some matrix, and you will be getting values at there. But in crank Nicholson, with this spatial term, we take the average of the two schemes. We compute at here the second derivative as well as here, and then we take the average of those two in order to represent this delta, like second derivative. But time, so you are computing at these two levels and averaging. So intuitively you can see say that you are calculating the derivative at the central point. So that is why this time derivative is calculated. It is said that it is calculated at the middle point, k plus half level. But like you do not have grids. Suppose your data will be in your data file will be having some rows and columns. Maybe this x, maybe this one is time. Like if you want to compute in computer, like in MATLAB or Python, whatever, you will define one array for time and one like for x, and your data like this one solution matrix will be a 2D array, and in that array integer numbers can only fit, like first row first column, first row second column, like that. But you are saying that no, you have calculated at half level, but you cannot represent that in computer or in the data file data array. So it is actually like down thrown. You you intuitively calculating at the half level, but you will put that value at the first level, like the initial level, and its average you will be using for the this one. You will be using the average, and for time you will be using the stepping like this. So I think C will be the answer. You have already mentioned C. And this one is one world question. Can you do this one for parabolic case? What, like what is the region of y. You have to do that one, b square minus 4ac. And for parabolic condition, like parabolic, it should be equal to 0. So tell me the answer for this one if you are doing. Like for this expression to be 0, these two terms has to be separately 0. So x square y square or xy should be 0. So this can be satisfied if either of them is 0. So maybe x equal to 0 or maybe y equal to 0. Again this term should also be 0, x square plus y square. Now this also needs to be satisfied, either one of them should be 0. So if one is 0, then other is automatically becoming 0. Similarly the vice versa. So this would be the answer, that both x and y are 0. Yeah, have you followed? Again, similar question. This one, yes. Time derivative is replaced by forward difference and space derivative is replaced by central difference. Okay, so again you can do this. You have to insert the value. First you have to determine the scheme: forward difference for time, central difference from for this one, special derivative. Then in that scheme you have to put the value, and from that expression you can find the value of xi. So you can again solve this one. Are you interested in doing this one? Okay, so you can try later on. So can you tell me the difference between different schemes like explicit, implicit, Crank-Nicholson? Yeah, suppose for this one, diffusion equation, you have these two. This one is explicit, this one is implicit, and there may be also Crank-Nicholson type. What is the like main difference? There are many differences. You can unmute and answer. So one thing is like the stability problem, stability issue. uh, Implicit and crank nicholson. Crank nicholson is also an implicit method. So implicit method is also always stable, whatever you choose for the values of the delta t and delta x. But for explicit, there is some criteria, like it is not, you cannot always use, like whatever, suppose you chose a very sparse grid, delta x may be 5 minus 10, 5 0 plus 10, then the scheme may not be stable depending on the criteria. But one thing is that if you use explicit scheme, you see it is much simpler. You just use the like present values, you can directly compute the past future value. But here it involves a solution of matrix, so this one is more computationally cost costier. It may happen that there is some problem with the matrix A, but in general, like I have like tried to mention you that you can solve like this. But if it is not, then you can use other methods to solve the equation. This is the main equation, you have to solve this one. You can use any methods to solve this equation. So similarly for crank nicholson as well, like where is that scheme? Yeah. So what is the answer? C. This one is the scheme. So if this is the scheme, again you can see, you can construct one matrix here, like this one, where you see all are having k plus 1th level, k plus 1th, k plus 1th. So some matrix will be coming here, and here you will be k plus 1th vector, like vector of these values. And on the right hand side again some matrix will be coming, and your u kth will be there. So you can again solve this problem. Suppose a u k plus 1, and this one is suppose b uk. So again you can solve this one to calculate this vector from the given uk. So here, like these schemes are in that way more involving. Yeah. So matrix inversion is costlier in terms of computation power. So explicit scheme is sometimes used in that way, like, but if you satisfy the stability condition, you can use the explicit method to solve the problem. Yeah, in that sense as well. So now if you like, you want to ask any questions, you can ask. I think these problems are over. So have you submitted the week 2 assignments? I think the date is over. I don't know. Are you asking anything? You are not audible. You are not audible. Okay. Yes. Procedure on. Procedure on what? You are not audible. Not able to. How we end up with the du dt ij plus half or du I du dt at I and j plus half. Okay, and du ij half minus du ij. Okay. Mm, so you mean, let me tell you which one. In crank Nicholson, this this derivative j plus 1 and j, and this one is like what is this, that one. Okay, you now stop sharing. Your question is how we end up with. So yeah, this is this thing we are doing now. So in crank Nicholson, we, if my grid is like this, or suppose K. So you want a scheme for this equation, but you have seen there, like for implicit scheme, you are using the central difference, and for this one, you are using backward difference, time derivative. Backward means your level of computation will be here, and you will be using the previous value, present minus previous value. But in crank Nicholson, for this one, the special derivative, I guess, you are using. So if I try to write this one, u I plus 1 at k plus u I minus 1 at k minus 2 u I k by delta x square. This one, like you are using for explicit or implicit schemes. Now instead of using like the computation at only one particular level, you are also using k plus 1 at k plus 1. So this one is also your derivative as well, like this one is also your del 2 u del x2. This one is also, but they are computed at different time levels, at here and here. So now you are, what you are doing, look, let me take the average of these two. So you are taking the average of these two to represent the same thing, del 2 del x2. So now where you will put the values, like you have taken the average and like to represent the special derivative, second derivative. So you can think of like I am calculating at this here, where I am using the average of the computed values at here and here. So your time, this one, your what is called this time derivative, it should also appear at this middle point. So you are using the central difference, you can assume like that, that you are using at I k plus 1 minus u I k, but that k is your like below point, considering this as the your level of computation. Is it coming like this? No, this 2 is not there. Why the 2 will be there? Because this one is a delta 2 by half, like delta 2 by 2, delta 2 by 2. So your delta 2 by 2 into 2 is coming. Cannot get that by saying what is right part is clear. Okay, so for right part, like where you are computing at the middle point, so you want to calculate the time derivative as well as in the that level, k plus 1 by 2th level, and there you are using central difference formula, that's it. So now you're like using half steps, your delta t now becomes delta t is actually delta t by 2, delta t maybe 1, your time separation is actually delta t by 2. So delta t by 2, again delta t by 2. So your central difference formula is, what is this? The future value minus past value, like one step ahead, one step um, below, divided by 2 into your time separation. But here your time separation is delta t by 2 uh, at this level. So 2 into this, so these two getting cancelled. So it is coming like that. So is it clear? Or is there any confusion? Okay. So the concept is that like, instead of using only at a particular level, I'll be using values at two different levels. So if I use more data, the accuracy will be more, we can expect from that. And also we are using the central difference. So for time derivative, the order is again it becomes higher. Here it is already yeah, here it is already second order. Time is also became second order because of considering the half step value. Okay, so this is the main funda for this Grant Nicholson. Is there any other, like maybe I can, not today, maybe next session I can also discuss. Do you have any more questions? So are you planning to like Have you tried to code these like solution techniques? Maybe suppose that a diffusion equation. So do you know MATLAB? You can use MATLAB to code this one as well if you want. You mean Crank Nicholson? The method that are developed in lecture. Okay. So if you are like interested, I can show you a few example codes maybe in the next session. For suppose for this Crank Nicholson and as well as the other explicit and implicit considering the stability criteria. So I can like I will show you quickly the code and the results like what is coming, and maybe the issue like when the scheme is not stable, you can like what is coming in case of unstable situation. Okay, I will include that in the next session for this diffusion equation. Okay, any more questions like no? Okay, if no, then let's end the session here, and we'll again meet on Sunday. Okay. Okay, so thank you. Thanks.